hello.
Hello.
Okay, so you're going to be low naturally. Just keep talking to me real quick while we do a sound check. Just,
Okay, so I did what you suggested on the video. I turned that thing all the way down. Um, I can change it
no,
if you would
you're
like.
you're good. I'm adjusting your volume compared to mine.
Okay,
And so you're actually pretty good. Keep talking to me real
awesome.
quick
Okay.
though.
All right. I hope that this all looks okay.
Looks great actually. No one can see it right now.
Ready?
No one can see
Yeah,
you right now.
I know.
Okay.
I have your stream in another window muted at the moment, but
Okay.
yeah.
All right, I think we're good, and I can go ahead and try to capture this the way that I tested before. We'll see how well it works.
Alrighty.
And properties.
I'm gonna be drinking tea, so you know.
Oh, it's okay. I think it's because I've got your lovely guest pick above it. Yeah, there we go. It worked out lovely. Thanks to Neuro. Neuro helped test me. We were testing this before stream. So there's Dr. Katie Mack, guys. And you can see me on Discord. So, but I usually look over here where I'm seeing chat and interactions, and I see you as well. So it's like I'm talking to you over here. So if I were to see you on a different monitor, you'd be up here, and that'd be really awkward to sit here and talk to you like that. So
Okay.
I have you at a few monitors. And everybody can hear her okay, right? Everybody can hear Dr. Katie Mack just fine, I hope. And this is Dr. Katie Mack. She, like I said, she is a theoretical astrophysicist, but specializing mostly in cosmology, so a cosmologist.
Yep.
Yeah, so she has a book coming out, and that's been something you've been working on for a while. When we had you on here, what was that, 2 years ago? Over that.
Must have been a while, yeah.
You were just starting on this, and when you were talking about it, you said, well, I hope it's going to be out, it was still a speculative time, but you were right. You said 2020.
Yep.
And
yeah, it was supposed to be out June 9th. June 9th was the original production date. And it's ready. Like, there's no reason it can't be out except the pandemic.
Yeah,
so,
right. That thing.
I got all my stuff in on time, but the world is doing something else, so it's been pushed back, and it'll be out in August. But this is what it looks like.
Look at this, guys.
So this is my advanced copy that they gave me to show people. It'll look like this. It's a cool cover. These little sort of lines on the cover, apparently they're going to make those with like copper leaf or something. It's unclear, but they said they were going to try and do that. So it might even be sort of a thing you can touch in a cool way.
Ooh, that's fancy.
I'm excited. I like the cover. I
love the
cool.
cover. The cover is great. Yeah. And I had a chance, like she gave me a copy of the ebook, and I did read a lot, more than I read it before my stream. And I ended up doing some bad math on my stream yesterday because my brain was already just so, like, I went into the vacuum decay. Cool. I decided to take it super light, and I was like, I'm just going to go straight for the vacuum decay.
Awesome.
But, and you guys have no idea what I'm talking about. And she will go through all of this. But yeah, I'm first curious to know, because I know you're still actively in research. Like, how does this?
Yes.
How is that influenced by the pandemic? I'm curious about this.
It's weird. So right now I'm in Canada. I'm not normally based in Canada. I'm normally based at North Carolina State University.
Yep.
But this semester I've been visiting the Perimeter Institute for Theoretical Physics. And the idea behind the visit was that I would hang out at the institute, talk to people, go to all the seminars and things and share ideas and start new collaborations. And then the institute shut down with everything else. And so now I'm in an apartment nearby all the time. And I'm still going to seminars virtually. And there are some cosmology group meetings and things like that we can do virtually. But I'm just in a room.
Right.
And so fortunately, the kind of research I do, there's no reason I can't do it alone in a room, because it's theory work. So it's writing down equations, it's coding stuff up, it's reading papers, it's talking to people. I can talk to people through Skype or Zoom or whatever. So it's certainly less efficient
Right.
to have everybody kind of isolated in their own little boxes, but work is still getting done, especially for us theorists who don't need to go to an instrument or like be at a
Right.
telescope or anything like that. So some of my colleagues who do experimental work, it's a lot more of a problem for them because they can't access their experiments and things like that. And a lot of telescopes are kind of shutting down for the moment. So my colleagues who do observations can't do those. But as a theorist, it's like it's a weird time, and everything is very distracting with all of the death and suffering and stuff, and
Right.
it's like that's rough, and
Yeah.
everybody's going through things with that. People are nervous about their own health and their families, and I know people who are going through things with their families, and like it's a hard time, and a lot
Yeah.
of people are not getting a lot of work done, for obvious reasons. But in terms of just the practical aspects, I'm in a much better position than a lot of people because I can just work here as
Yeah.
long as I can get my brain in order to
Exactly.
focus on
That's
the
it.
universe.
It's right. Like pulling away from what's happening here on our rock to going. That's
Yeah.
been a challenge for me as well. Something that I've actually very much struggled with the channel. Like there was a time where I was like, guys, I can't. Like it just feels like too much is too close to home, and when that
Yeah.
happens, you get distracted, and especially. Everybody's like, well, it's an escape. And I'm like, yeah, but it's tough to escape since it's so personal.
Yeah. I mean, I definitely, I've been telling my colleagues and stuff, my efficiency is not what it was
Right.
because I care about the world and people in it, and
Yeah.
that's, you can't just like be like, oh, okay, all this stuff is happening, and then pretend it's not and
Yeah.
do a bunch of equations. Like sometimes you can do that. Some people can do that better than others. For me, it's hard to just focus on the work. But there have been times when diving into a bunch of equations has been a beautiful and wonderful thing to be able to do as well. So it kind of
Absolutely.
goes back and forth.
Yeah. Someone just asked earlier, and I want to make sure that, so you'll see me do this referring to chat every now and again, but not obviously when you're in the middle of a thought. Is there going to be an
Sure.
audible version of your book?
Yes, yeah. So the person who's reading that is in a home studio doing the recording at the moment, as far as I know. So that's going on, and there's going to be an ebook. It's going to go into several different languages. So it'll be in a bunch of places.
Yeah. Yeah. So there you go, guys. So it will be widespread.
Yeah.
And what a word to choose when talking about the pandemic, just coming off of that topic. That's great. We're gonna, and also she has hung out with us when we do other things. And again, you're always welcome to do that when we have other. If you ever just want to dive in and take a break, Twitch is. I mean, there's a few of these streams on here, but not many.
Yeah.
But it's its own. It has helped me cope with a lot too. So.
Yeah.
But anyways, I do want to go into this stuff because this stuff that I was reading. So on your website, you list that there's 5 ways that the universe could die potentially, but
There's
you
there's
only
5 that I cover in the book. Yeah.
right, but you've only
Yeah.
teased really 4, and everything else that I've seen you. I know these
Yeah.
numbers aren't matching. And I don't want to.
Yeah.
I don't want to drop information I know already about your book, because
Well, so the reason for that is so the four that I talk about when I give talks and stuff, I choose those because they're a little bit more straightforward to explain.
Sure.
And then the 5th is one that's there are several different versions of it, so it's a little bit more complicated from that point of view, and the mathematics behind it is more complicated. So
But
the
you have a
reason that I choose those
blackboard. You have a
four, I
blackboard.
do have a blackboard. That's true.
In a geodesic model, and I'm seeing all the things already there. I love it.
Yeah. But yeah, so the book goes through Big Crunch, heat death, Big Rip, vacuum decay, and a bouncing cosmology. So
There's
the
that.
one that I don't,
Yeah.
the one that I don't talk about as much in other things is bouncing cosmology. It's just because there are lots of different ways you can go through some kind of cycle in the universe, so like a big crunch, big bang kind of cycle, or there are even some where you have like universes crashing into each other and bouncing off and creating big bangs that way, and there are some that sort of cycle through in other ways. So the bouncing one is sort of the most diverse, and it takes the longest to explain. So that's why I usually go through the first four. But
I
also,
gotcha.
you got to leave something for people to want to
Right.
read the book for, right?
Yeah, people said no spoilers in here already.
Right.
And guys, just so you know, I'm probably going to reserve like the last 10 minutes of us talking. I'm slating us usually for an hour just because that's, I mean, unless you have more time and you're like, no, I can go on longer. I don't want to assume people's time because, again, she still is doing research. And so, it's not like her day is just completely freed up because she is also a science communicator too. So what I do here, but she's involved in, her hands are in all of this, the research, the SciComm, all of it. So we'll have questions towards the end. I see people already are asking questions. Roger Penrose is being brought up. All right. So,
Yes.
And that's because I have a wonderful chat. So I have my demographic are people that really know a lot about space. And then I have people that really don't know much at all, and they're hoping to learn more. So with that, I think we should start talking about cosmology in general,
Okay.
and what cosmology really is. And I'm going to ask you some questions I've already talked about on here, but your perspective. This is why we have you here.
Yeah, so cosmology, the way I define cosmology is it's the study of the universe as a whole. So from beginning to end, the evolution of the cosmos over time, the constituents of the cosmos, what the cosmos is made of, the basic function of physics in the universe. So all of that kind of falls under the umbrella of cosmology. And depending on who you talk to, like there are people who do a lot of different things that they would classify as cosmology. So one person might study, the very, very earliest moments of the universe and different ways that might happen. And that would be somebody who does early universe cosmology. Then there are people who just study very distant galaxies. And because they're distant, they're also farther in the past because of the time it takes light to get to us. And so they would be cosmologists studying like galaxy evolution or something. And then there are cosmologists who are basically string theorists who are just studying sort of the mathematical structure of the cosmos, and people who do what's called experimental cosmology, which sounds dangerous. But it's actually sort of it's because most of the people who started working on experimental cosmology were experimental physicists and then got into cosmology, and so that's it's more of a sociological thing than actual experiments, but it's studying things like the cosmic microwave background, which is the kind of afterglow of the Big Bang. And so you do an observation, kind of an experiment of observing the universe in a certain way, and that's a kind of experimental cosmology. So
would you
there are lots of
group
different
people
areas.
in at CERN as being a part of that experimental at the
So,
LHC?
Right. So there's a theory group at CERN who, and they do a lot of cosmology in the theory group at CERN. So a lot of sort of connecting particle physics to the way the universe works, and people just working on aspects of astrophysics as well, in the theory group there. But then people who work on the experimental aspects, the experiments themselves, I would say that's experimental physics, but often with applications to cosmology. For example, there's an experiment there that is basically a telescope pointed at the sun, but with the lens cap on, and that's looking for particles called axions, which
Yes.
might be a kind of dark matter, and they might be able to transition between axions and photons. And so you point this thing at the sun, you put the lens cap on, you put a big magnetic field in there, and you hope that some of the photons coming from the sun will turn into axions, go through the magnetic field, come through the telescope, show up as photons again on the other side. It's wild, but it's basically astronomy, but with this sort of weird aspect to it. And so there are a few things like that where people are looking at stuff like antimatter, or people are looking at the properties of the Higgs field, which is this energy field pervading all of space. It has to do with how things happen in the early universe. And all of this is connected to astronomy, to cosmology. So the boundaries between these fields get really blurry, because so much of what we're learning about the universe comes from particle physics and vice versa, really.
Yep. Yeah. And someone even said, so how's that a part of astrophysics? So astrophysics is more of an umbrella, and it encapsulates all these other. So cosmology, the way I usually say, is like the study of the very large. But also cosmology, like Dr. Katie's been saying, is that it also incorporates the study of the very small. So quantum mechanics, so QM.
Yeah. I mean, so the stuff that I work on, I study dark matter and the particle physics of dark matter. Which
so very light topics.
Yeah. But that's, dark matter is something that seems to be this invisible stuff that is all over the universe, collects in galaxies and stuff. And we know it's there because of its gravity, but we think it's probably some new fundamental particle, and we just haven't been able to detect that particle. We don't know what that particle is, but it probably does have some kind of particle physics. And so part of what I work on is trying to understand the connection between the particle physics of dark matter and what it does out there in the cosmos. Yeah, so there are a lot of places like that where, and if you study the early universe as well, you're studying the time when the whole universe was very hot and dense and a lot smaller in some sense. And then you need to do a lot of particle physics to understand what's going on there.
Yeah, and what you're referring to actually is what we would call the hot Big Bang, right? So when the universe was much smaller, like you just actually defined the hot Big Bang. So a lot of people, when they hear that word, they get confused, because I think a lot of times people be like, in my channel at least, and again, this is, they'll say like, oh, well, there's the singularity, and then something came from nothing, and then but when you talk to people like yourself, that would be a little bit different.
Yeah, and the whole singularity thing, I was actually just earlier today, I was working on an article for a magazine where I was explaining a little bit about the singularity idea and how we think the universe started, and all of that. And we don't know if there was a singularity. We don't know if there was ever a time when the universe was infinitely dense. Certainly, it probably wasn't ever infinitely small. There's a ambiguity there in how you define it, singularity, but we do know that it was at some point much hotter and denser, and in some sense smaller than it is today. And that's what we call the hot Big Bang. And so the TV show The Big Bang Theory, the beginning of the theme song for that is actually a really good explanation of the Big Bang Theory.
So I've never actually watched it, and that's terrible to say as a science communicator.
No.
So, but I'm interested to hear why.
Things
why
about
is that?
So there are aspects of the Big Bang Theory TV show that are awful. So anyway, I'm not going to get into that. But the theme song starts out, our whole universe was in a hot, dense state. Then nearly 14 billion years ago, expansion started. And that's hot Big Bang Theory. That's the Big Bang Theory. The whole universe was hot and dense, and expansion.
Sounds good to me. Yeah, that sounds great to me. It's a terrible show. Oh my God, guys. Well, then I don't too.
I don't watch the show, so but I do know the theme song. I've seen a lot of the show, so anyway.
Yeah, that sounds good. Now everybody's like, I'm curious. I didn't think it was that bad, guys. This is when we can invite her. She'll just maybe come in sometime when she's in between research, and we could talk about this. So leading into that, so we talked about cosmology for a bit, and I think when we talk about cosmology, so I had a few people yesterday because we kind of did like a prep. We were going to talk about Pluto, but then I was like, well,
Okay.
we're going to go ahead and do some prep so everybody knows, what kind of
Excellent.
topics will be covered to a
Yeah.
degree. And again, there's certain things I don't touch. So when I talk about, I don't
Okay.
talk about the Big Bang because I feel
Okay.
like in pop culture, pop sci, there's so many misnomers. There's so many, again, people bring up like the singularity or how does something come from nothing, and there's a limit to where I feel comfortable. Like in my SciComm, I'm very much if I don't know or if I don't understand, almost like the Feynman approach. Understanding something means you can convey it. So if you can't convey it properly, then you don't really understand it.
I think there are limits to that, but I think that it's definitely.
Unless I had cue cards.
I think it's definitely true that it takes a deeper understanding to convey something to other people than to just know it yourself.
Yeah.
But
Understanding
there
it
are also
in my head. Go on.
yeah, but there are also things that are just inherently really difficult to explain, and so the somebody could say, oh, I understand quantum field theory, and you could say, oh, well, explain it in simple terms, and you'd be like,
Yeah, exactly. That's another thing.
You can't necessarily do that.
Right. QFT I dodge too. So I have a few. QFT I'm constantly, bobbing and weaving. Where people are like, why didn't we ever do a QM stream? I'm like, we can listen to other people talk about it. People that are actually in the field, and I don't want to, because I have a lot of respect for people like yourself and other people that work in for instance QFT, where I don't want to misspeak. I don't want to say or paraphrase incorrectly, but that's something they teach you in academia. That's something I really appreciate. So you don't want to misinterpret something that someone says and
Right.
take it as your own and then convey it that way. And that's something you got to be really careful with SciComm.
I think it's really important not to overreach in terms of like just making stuff up if you don't really know.
Right.
I think it's important to be really honest about the limits of your understanding, and to not like gloss over stuff and just be like, oh yeah, you don't need to worry about this. I understand this, whatever. Like, I think it's it's useful to be clear about like, here's what we understand, here's what we don't understand, here's what I can explain, here's what I can't. This is where you can look for more answers. Like, I think that all that stuff is really helpful. I don't think it's helpful to just be like, oh yeah, I know everything, and
Who would ever listen to that person? Many people. That's what that was. So here, as far as like things like, I'm sorry, I love that reaction still playing in my head because it's a perfect thing. Because I so much, yeah. Look at the chat. Can you see the chat already?
Yeah.
It's already so okay. So talking about cosmology, so it's the study of the very large is how I usually say it, which as you put more like, I'm laughing still, you put more into like the beginning and the end, which is they're intertwined heavily, and that's a great way to even specify further, to kind of go into more detail about what I mean by the study of the very large. So we can start with the age of the universe and like what we can actually see versus like size, because that's a little bit different. Then kind of go into some of the scarier topics that lead into some of the things that you're going to discuss in your book, like dark energy and dark matter.
Sure. Yeah. So in terms of the age of the universe, the best estimates we have now are it's about 13.8 billion years. And we know a lot about the beginning. So we have a pretty good understanding. Like, we can write down what happened from, something like 10 to the minus 10 seconds. So, a tenth of a billionth of a second, with really, really pretty good certainty. Like, we have a pretty good understanding of what happened from then on. And even before that, we have really good models and really good sort of theories about it. So our understanding is that something. Okay, so here's where it gets complicated.
Go ahead.
So maybe there was a singularity. We don't know. The singularity might have been a state of very high density, but not infinitely small size. So it could have been like an extended but very dense state. We don't know if the singularity happened or not, because what we think happened after that is something called cosmic inflation, which is where the universe started expanding very, very rapidly for a very short period of time. And that rapid expansion kind of makes it hard to know what happened before it.
Right.
But that would be at like 10 to the minus 35 seconds. So really, really early on. And then when inflation ended, whatever caused inflation dumped a whole bunch of energy into the universe and started the hot phase of the hot Big Bang. Mm-hmm. So again, we don't know for sure that inflation happened, but we think it probably did. And then the universe was hot and dense, and then it was still expanding, but not as quickly. And during that phase, a whole lot of things changed about the sort of how physics works, and the forces of nature started to distinguish themselves. The particles of nature that we know about now started to come up, and then atoms started to form, and then eventually this sort of fireball stage of the universe cooled, and then there was a whole lot of neutral hydrogen, and then stars and galaxies and so on. The one of the coolest things about astrophysics, about cosmology, is that this fireball stage, this part of the universe, the stage of the universe where everything was like hot and dense, we can actually see that. So when we look out into the cosmos, we're looking back in time, and so we can see galaxies that are billions of light years away. We're looking billions of years into the past, and if we look far enough away that we're looking, 13.8 billion years into the past, what we see is a kind of glow of radiation in every direction. Mm-hmm. So we see parts of the universe that from our perspective are still on fire, because the light has taken so long to get to us that it's the light from that initial fireball stage of the universe. So as you look farther and farther away, you see the parts of the universe that are so far away from us that the end of that kind of fireball stage of the cosmos is just happening there, and that light is getting to us now. So we can actually see the universe as it was when space was full of this kind of roiling plasma.
Right.
And we can study that light and the patterns in that light as we look at different parts of space and learn about how matter was coming together under gravity at that time, and how the first little bits of structure were starting to develop in the universe. And that's called the cosmic microwave background. And
right.
that's
I was
one
about
of the
to say,
most,
the heat signature, right?
Yeah.
It's that CMB.
Yeah. Yeah. And so that's one of the most important tools we have to study the early universe and to study what the universe is made of, because we can see what was going on at that stage. We can see how gravity was starting to pull things together, and we can learn about everything, how the universe has evolved from there to here. And we can put stuff into computer simulations and take that pattern in that early background light and then go from there to all the galaxies and clusters of galaxies we see now, just by taking that pattern of a little bit more density here, a little bit lower density there, letting gravity pull those things together and create structures like galaxies and clusters of galaxies. And then we get the kind of cosmic web of galaxies and clusters of galaxies that we see in the universe. We have a really good understanding of how that physics works. So it's very, very cool. It's amazing that we can actually see this stuff directly, that we can actually look at the afterglow of the Big Bang. We can look at parts of the universe that are still in the hot Big Bang by looking far enough away. And we see it as microwave radiation coming from every part of the sky. And that's an incredibly important tool for understanding the universe.
Absolutely. And so with us being able to see that far back, what about the size? Because a lot of people in here, when we talk about this and the expansion. So this is where I start to bust out my handy dandy tool for this. And by the way, hi, Michael, or not Michael. We have John Michael Gaudier in here, and he was asking questions. We're going to have questions at the end of this. But JMG's, you might have heard of John Michael Gaudier. He talks about a lot of this stuff on YouTube. But yeah, this is where I bring this out. So talking about the expansion and how that
That's
accounts
cool, yeah.
for, well, yeah, until it snaps in my face. It'll be, I'm going to wait. This is a good rubber band though. I feel like this is good quality. So,
Yeah.
but in talking about the size versus what we see, that's where it starts to get a little bit more complicated, right? I mean, you can explain it, I'm sure pretty well, right?
You mean the size of the observable universe?
I call it the Hubble bubble, but that's just because I found ways to talk about things. So like what you can observe. Yeah.
Right.
Right.
Yeah. So the Hubble bubble is actually a slightly different thing. The particle horizon, I think, is what you're talking about.
The Hubble bubble's an actual thing. I thought I was being cute.
Yeah.
Oh,
no,
gosh.
there's a Hubble sphere.
No.
And the Hubble sphere. Okay, get this. The Hubble sphere is defined by the distance at where things are receding from us at more than the speed of light.
Right.
But that's not the edge of how far we can see.
Right.
Because there can be things that are currently moving away from us at more than the speed of light, but because the light left those things a long time ago, the light is already partly here.
Yep.
And like it got toward us before those things were moving at more than the speed of light away from us, and so the light can reach us. So we see a lot of things that are currently moving away from us at faster than the speed of light. We actually see things that have always been moving away from us at faster than the speed of light, which is a weird thing that I would take a while to get into. I do talk about it in my book a little bit. So the Hubble sphere is where things are moving away from us so quickly that light that left them now would never get to us. Mm-hmm. But in terms of what we can see, the farthest reaches of the observable universe, what that's defined by is how far away light that left that point at the beginning of the universe, it would take the whole age of the universe to get to us.
Right.
So that's, so you would think that would be 13.8 billion light years, right? Because the universe is 13.8 billion years old, takes light a year to go a light year.
Right.
But actually, because the universe has been expanding since then, something that was 13.8 billion light years away a long time ago is much farther away now. So the current distance to the edge of the observable universe is around 45 or 46 billion light years.
Yeah.
So our observable universe is a sphere centered on us of around 45 billion light years in radius. And we can't see beyond that because something farther away than that, it would take more than the age of the universe for the light to get to us. So, but it doesn't mean that there's any actual edge. Like we don't have any evidence that there's any kind of edge or evolution in terms of like the space being different far away. Space, it seems that the more you zoom out, the more the same space looks, in terms of like you just have a bunch of galaxies and they look smaller when you're zooming out in some sense in a big picture way. But there doesn't seem to be any edge or any difference aside from the fact that there's a point where we cannot see past. And we'll never be able to see things that are beyond that because the expansion of the universe is speeding up. And so those things are going to get farther and farther away from us faster and faster and faster.
Yeah, I see people already talking about like the shape of the universe, like being flat or, maybe a hypertoroidal shape, space donuts.
Yeah. Flat is so the shape of the universe, like because our cosmos doesn't seem to have any edges as far as we know. Like our observable universe is a sphere because you go same direction the same distance in every direction you define a sphere.
Right.
But we don't see any reason to think that there's any edge anywhere. So it could just be infinitely large in all directions. And so in that sense, there's no shape to the universe. But when we talk about the universe being flat, what we mean is that light travels through the cosmos in the way that it would travel through a flat space. So what that means is that, two beams of light would stay parallel forever rather than if space were curved, they would come together or they would diverge. Yeah. So the curvature of space is what happens when matter exists in the universe. So that's what this
geodesic model
to show, like, if you have matter in the universe, it curves space around it, kind of sort of pulls it in toward itself, and so in the vicinity of matter, space is curved inward. But on the very largest scales, space seems to be basically flat. So if you sort of zoom out.
And so now we've got the size, and there's things that and we've already kind of covered some of them with dark matter and dark energy, and these are two different things. I see people talking about this. Like, dark matter is actually one. We'll start with that. That's kind of been like a little bit more. So we always thought like these galaxies were made up of dark matter. Like, our galaxy is 90% dark matter with a dark matter halo, right? Figures I'm throwing out from like things that I've read in the past. Any new research like in the last couple months, forgive me, but then we find these galaxies that contain, we believe, little to no dark matter, and that kind of flipped that on its head, because we were going around saying it in many documentaries, all galaxies have this dark matter halo, and they, that's what keep things in check, and the rotation rate of stars, and things aren't being flung out. But now that's kind of turned on its head a bit.
So dark matter is interesting. So every sort of reasonably sized galaxy, almost every galaxy in the universe that we've ever detected appears to have more dark matter in it than regular matter by a large margin. So, 80-85%, something like that, of the matter in the universe is dark matter, which is just invisible, right? It's some kind of matter that appears to be invisible. And the fact that it's invisible is connected to the fact that it behaves weird, which is that, so if something is invisible, that means that
it doesn't interact with, it doesn't interact with us, right?
It doesn't interact with electromagnetism. So it can't like bounce off of us or be deflected by us, because that's all electromagnetism too. When you touch something, it's your electrons pressing against the electrons of the thing you're touching. And if dark matter doesn't do electromagnetism, it doesn't do that. So it can pass right through us, it can pass right through itself, other matter, all of that. And so when you look at its distribution in the universe, it sort of is more puffy, whereas like galaxies and things become flat because the interactions create flat disks instead of round things on large scales, like for galaxies and disks and things. Anyway, so we're pretty sure that most galaxies are massively more dark matter than regular matter. It's this invisible stuff. It's holding the stars in. It's holding the gas in. All of that. But there have been a few galaxies that have been detected recently that are small galaxies that seem to not have dark matter, or seem to have no detectable dark matter, in terms of, like, if you look at the way the stars are moving around, it doesn't seem like dark matter is necessary in some of those little galaxies. And if that's true, if they really don't have dark matter in them, then that's actually better evidence for the existence of dark matter.
Right.
So the reason for that...
Yeah, go on, please, go on.
Yeah, so the reason for that is that some people have suggested, like, what if dark matter is not real, but actually gravity just acts differently than we expected, and so you just have regular matter, but it's held together more strongly because gravity is being strange, and so it makes it look like there's dark matter. But if that were true, then every galaxy would look like it had the same sort of amount of dark matter, right? Like it would, like, you wouldn't be able to have two galaxies that have the same amount of regular matter but different amounts of dark matter, right? Like that just wouldn't make sense,
right,
if dark matter were an illusion. There are other reasons to believe that dark matter has to be a real and separate thing. When I give colloquium talks about dark matter, sometimes I go through like 13 different pieces of evidence. They're all unique and all point to the same
13.
The same thing, yeah. So it's not just the way that stars move around galaxies. There's a whole bunch of
gravitational lensing, or
right. Gravitational lensing, and then the structure of the cosmological background, and then like just a whole bunch of different pieces of evidence. So we do have pretty strong evidence that dark matter is real. But if these little galaxies really don't have dark matter in them, if these few that have been detected, then that's even more evidence. But that there's there's still arguments in the literature about whether or not those things really don't have dark matter. But they could be formed, basically they'd have to have a different formation mechanism, because most galaxies, like the dark matter and the regular matter, come together sort of together early in the universe, and then the dark matter kind of helps bring the regular matter in to form the galaxies. And so it's quite hard to make, it would be really hard to make a galaxy like ours without dark matter. Our galaxy wouldn't exist without dark matter, because if it were just regular matter, it would bounce off and not come together in quite the same way.
Yeah. So regular matter, guys, I always tell you it's baryonic. It's a 5% of everything, and we're a part of that 5%.
Yeah, because there's dark energy too, which is like 70%.
Yeah, and you do the same roundings that I do. Last night we were watching this, and we were because I did bad math again, because I had read some of her book and it was so captivating, but my brain melted. But that's a good thing. I look for that. That's a good thing. So I know that I brought up dark matter, but I know that's something that, like, it's so exciting to talk about dark matter, even though we know so much and so little. Little. But it's more, we know more about dark matter than we do with dark energy. And dark energy has a lot to do with some of these things. So with your book and talking about how the universe will end, let's go in with like the one that you feel is maybe most probable.
Yeah. So the most likely one is definitely the heat death in terms of what we can see now and what we can extrapolate to in the future. So the heat death, it sounds like a misnomer, because you can also call it like the big freeze. It's a scenario where basically, like, right now the universe is expanding, galaxies are getting farther apart from each other for the most part, but that expansion is speeding up, which is weird, because you don't expect that, right? Because all the galaxies should be sort of pulling back toward each other. All the gravity of everything in the universe should be slowing the expansion down. That's what the equations to general relativity say should happen.
Didn't that happen at some point? Wasn't that at some point? Did it not just slow down? Yeah.
It was slowing down. Yeah. So from the end of inflation until about 5 billion years ago, the expansion was slowing down because all the stuff in the universe was kind of pulling back. And then about 5 billion years ago, the expansion started speeding up. And we don't know for sure why that happened. We call whatever made that happen dark energy. And it might just be what we call a cosmological constant, just a property of space, that space, the more space there is, the more expansion it does.
Right.
That might be what it is, but whatever it is, dark energy is the term we use to refer to whatever is driving the accelerated expansion. And if it keeps going the way it's going, in a way that it looks like a cosmological constant, then over time, galaxies are going to get farther and farther apart from each other, faster and faster. And so eventually, like, each galaxy or little group or cluster of galaxies will be sort of isolated on its own. So we're in a group of galaxies called the local group, which includes the Andromeda Galaxy and the Triangulum and a couple of little satellite galaxies. So our little set of galaxies will be together because we're already gravitationally bound, but distant galaxies will get farther and farther away, faster and faster. And in about 100 billion years, we won't be able to see other galaxies because they'll be so far away. They'll be sort of carried away from our, they'll exit our Hubble Sphere. They'll be moving away from us at faster than the speed of light, and we'll stop being able to see these other galaxies. And so our universe will get darker and darker and colder as the universe expands faster and faster. Other galaxies won't be bringing in new gas to form new stars, so the star formation in the cosmos will slow down. It's already been slowing down.
Yep.
And then the stars that we have in our galaxy will start to burn out. We'll use up the fuel and burn out, and then there won't be any new stars being born, and there will be all these like old stellar remnants. They'll start to decay, and particles will start to decay, and black holes will start to evaporate, And
wait,
eventually,
you can't, but the Hawking radiation, right? You can't.
Yeah.
So let's stop at that.
Okay.
So black holes evaporating. What is
Yeah.
what?
So this is something that Stephen Hawking described in the 70s, where if you leave a black hole alone long enough, then it'll kind of radiate particles and energy and shrink over time. And it takes a really long time, especially like for the larger the black hole, the longer it takes. But when it starts to get smaller, it speeds up and speeds up. But it's a quantum mechanical effect, basically.
Right.
And it has to do with virtual particles. And there's a whole explanation in A Brief History of Time, which is not a particularly good explanation, because
I've had
in the
to
sense
read it
that
a few times.
yeah, I mean it's not a good explanation in the sense that it's not very accurate. But I talk about it a little bit in my book too. But anyway, it has to do with the way that particles and waves are interacting with the very extremely curved space around a black hole. But the upshot is that you get a little bit of radiation off the edge of the black hole, and that makes the black hole reduce in mass. And so it just kind of radiates away its energy, and it's called Hawking evaporation. And so if you leave a black hole alone long enough, eventually it will disappear, and just create a bunch of radiation and vanish. And so anyway, so that happens in the distant future of the universe, and eventually you have a universe that has basically nothing in it. It's like all the particles are decayed, the radiation is being dispersed through the cosmos, and you have just a whole lot of cold, dark, empty space, and that's when you get to the heat death.
And so why is that like the most plausible? Why is that the most likely, I guess?
Because if we just look at what's happening now in terms of the expansion and the acceleration of the expansion, and we apply what we know about general relativity and how that governs the evolution of space, the expansion of space, then what you get is this cold, dark, empty cosmos over time. Like that's the end result of the kind of expansion that we're experiencing now. And I should say the term heat death, the heat there refers to like waste heat, basically. So in physics, disordered energy is heat, and what happens in the heat death is that all of the structure in the universe turns into this disordered energy, just decays into heat, and it's cold, like it's not very much energy, but it's disordered, and that's part of this whole picture where the second law of thermodynamics says that entropy increases over time, that disorder can only increase over time. And so as you get to the closer and closer to the end of the universe, the disorder in the universe increases, everything decays into waste heat, and at some point all you have left is this background heat, this like heat bath at the very, very low temperature. But because it's heat, it can't be used for, like, it's not useful. Nothing can happen really. Like you can't do, useful work with it. And you can't, and because the entropy can only increase, you can't create order out of it. And so nothing can really happen anymore at that point. And you get into all these weird ideas about the arrow of time, because in some ways of thinking about it, the way you define past and future is that the past
changes,
is
right?
less, like the past is less entropy, the future is more entropy.
Right.
And so if you get to a point where you have the maximum of entropy, then what is the future? Like there is no future anymore.
Boring, right?
The arrow of time just stops.
Exactly. There's not going to be like much to differentiate between the two at all.
Yeah.
So
and so that's a pretty solid end of the cosmos, if you ask me. I mean, space is still there, but
it's still there.
Like, what does it even mean?
Right? What does it even mean? So true. And is there any other way that we experience this kind of like heat, that energy, in any other of your end of universe theories that you talk about?
So there are other theories. The other theories that I talk about in the book have some have sort of similar evolution in terms of dark energy, dominates the evolution of the cosmos. So you can have a situation where dark energy could be something sort of more extreme than a cosmological constant. And in that case, it can kind of pull apart galaxies and even planets and then all of space, and that's called the Big Rip. So that would be a very dramatic end that would you wouldn't get to the heat death, but you would rip apart space and everything in it.
Seems nice.
In a finite time. So that would be bad. So that's the Big Rip. And then if you have dark energy being really weird and being something that can turn around, where you instead of doing expansion, you can turn around and become a force for contraction. If that were able to happen, then you could get to a big crunch, which is one of the scenarios I talk about, where the expansion of the universe would stop and turn around, and all of the galaxies would crash together again. And that one's fun because you get a very interesting sort of kind of death.
Yeah, there's some cool
scenario.
stuff about that one. There's some real cool stuff about your description of it.
Yeah, because what happens in a big crunch scenario is, galaxies collide with each other. That happens all the time in the universe. That's not that big a deal. Like when galaxies collide, it brings together a bunch of gas, you get new stars forming, but the stars themselves don't tend to hit each other because there's just so much empty space in a galaxy that the stars get kind of mixed around, but they don't collide, right? And so a galaxy collision is not fatal to a solar system, for example. I mean, our galaxy is going to collide with the Andromeda galaxy in about 4 billion years.
Right.
It's coming for us now at 110 kilometers a second. But when that happens, the solar system will be basically okay. The Earth will already have been destroyed, but whatever. The sun will be all right. The sun will be dying anyway. But in a big crunch, so not only do you have a bunch of these galaxy collisions and stuff, but also because space itself is contracting, all of the radiation in the universe is getting intensified, right? Because it's being contracted to higher energies, to smaller wavelengths. Blue shifted is what it's called, but it means that infrared light will be compressed to visible to UV and gamma rays and so on. And so all of the background light from the Big Bang will be brought back together, right? So we'll get into that hot dense phase again. But even worse, all of the light that all the stars in the universe have created all of the years, and all those sort of high energy radiation from black hole processes and stuff like that, all that radiation will be compressed too. And so what ends up happening is that all this compressed radiation comes together in the universe and starts to ignite the surfaces of stars. And so you get thermonuclear explosions around the surfaces of stars just from the background light of the universe being compressed, and that's what kills the stars. And then it's all over. You can't survive that. So right. That's a very dramatic way to go.
Yeah, and so people, I saw someone say that where was it? So with galactic collisions, so when Andromeda and the Milky Way collide, going back to even that before the big crunch, right? So it's going to take those celestial objects and start working on them first as a part of the universe, right? But stellar collisions aren't very common, guys. At least what I understand, you can confirm or deny, but they're not. When galaxies collide.
No. It's very unlikely that any two stars will collide, even if galaxies totally smash into each other. The only places we know about where we think that stellar collisions happen is sometimes in very dense star clusters. Sometimes in very dense star clusters, we see these stars that are they're a weird color for their age, and they act differently. They're called blue stragglers. And we think that those are formed from the collisions of stars, but they only happen in these really dense star clusters.
Yeah, I usually like to say they get yeeted. That would be something, so they get a gravitational assist and get kicked out potentially of said galaxy if they get close, but the actual collision, guys, is pretty uncommon.
Yeah, you can fling stars, light years and
All
light years
over.
away with galaxy collisions. I mean, there are these. You can find images of interacting galaxies, and it's a fun thing to search for, like colliding galaxies, interacting galaxies, and you see they have these like streams of stars spreading out from like stuff comes in and it gets flung out, and it's very cool looking.
Yeah, no, and that's one of the things that gets talked about a lot when I talk about the Andromeda Milky Way merger. People are like, oh my God, what about Earth? What about, we're going to get flung out or we're going to collide with another star? I'm like, no, it's okay. It's okay. And you won't be like, again, we're talking so far in the future that the oceans will be already evaporated off of Earth. And but so we have the big crunch, and then we talked about the big rip, but then your favorite, I think, is vacuum decay, and that's why I went to go read it.
Yes. Yeah. No, vacuum decay is definitely the coolest one. So vacuum decay is something we know about. And you might need to use your
board, by the way, for this one, because this one.
Okay. Yeah, I can use it. I can do that. Yeah. So vacuum decay we know about because of particle physics. So vacuum decay is an idea that's been around for a really long time, where it has to do with the Higgs field. So the Higgs field is this like energy field that pervades all of space. The Higgs boson is an excitation of the Higgs field. The Higgs boson is connected to the Higgs field. And this is, so the Higgs field is something that basically changed the laws of physics early in the cosmos, right? Mm-hmm. So in the very early universe, the Higgs field evolved in some way. The value of the Higgs field changed, and we ended up with a cosmos that we can live in. The laws of physics adjusted so that we have the strong force, the weak force, the electromagnetic force, like the different forces in nature came out of the properties of the Higgs field. That's how it's all connected. And so the Higgs field is governed by what we call a potential. So a potential is like, it tells the Higgs field what kind of value to take, and I'm going to draw a picture of that.
Yes, so please do.
I'm gonna assume that y'all are okay with getting a little bit technical here.
They're gonna be because I already prepped them for this. And the Higgs field, again, guys. So you have the Higgs boson and the Higgs field. These are two different things, and like she said, there's an excitation. So excited. It's a fancy word for being excited.
So the Higgs field in the early universe had a potential that looked like that, where the Higgs field was like, you can think of it like a ball in a valley, like sort of settled into this place. And then something happened in the early universe, and it changed the potential to look like that. And the Higgs field showed up in a different part of that potential. And so the value of the Higgs field is on this axis. So the Higgs field got some other value by sitting in that part of the potential. Now, so we're sitting there, we're all good. I'm gonna draw a picture of this. So, imagine we're right here. We're sitting in this part of the potential, and this potential like governs the value of the Higgs field, which tells us something about the properties of space, of physics in the universe. Now, it's possible that there's some other like valley where the Higgs field could live, like that. And if that's true, then, and if that valley is like at a lower energy, then that means that the Higgs field would kind of rather be over there. Okay, so you can think of it, you can think of the analogy of valleys and balls rolling around in valleys, right? So there's the valley, and we might be stuck in a little sort of divot in the edge of this valley, this larger, sort of in this potential. So what that would mean is that this is a different, we call it a different vacuum state. So the vacuum state is where the Higgs field is, and what that tells you about the properties of the universe, the constants of nature, and how physics works, how the forces of physics fit together. And so if we're here, this is a false vacuum.
Yeah, someone's asking what is the Higgs field again? Because it is, I understand that it is hard to understand, just like in layman's terms. And then that versus the Higgs boson and how that contributed.
Yeah, so the Higgs field it's just an energy field that pervades all of space. So it has a value. That value is associated with like how much energy is in that energy field. You can think of it that way. And the different kinds of particles interact with the Higgs field, and the interactions of those particles with the Higgs field are connected to how those particles have mass, like how they experience mass. So if a particle interacts more strongly with the Higgs field, that's a heavier particle. And if not, then it can be lighter. That's a sort of rough way of thinking about the Higgs field.
Yeah, I think.
But the value of the Higgs field, whether it's along this axis. So this axis is like the value of the Higgs field. If the value of the Higgs field is over here, that tells us something about how the forces in nature work together, what the constants of physics are, things like the mass of the electron or whatever. If the value of the Higgs field is over here, then that would change all of these things about how physics works. It would change the masses of the particles, the interactions between the particles in a way that would be really bad, right? Because if the Higgs field is much bigger, then basically what would happen is that we would be in a space where our particles couldn't interact with each other the way they currently do. So our particles wouldn't hold together, but also like it would be kind of a heavier space, and the space would collapse on itself. It would be something called de Sitter space, which isn't really stable.
Right.
So you definitely don't want the Higgs field to be over here. But if the potential is set up this way, if it's such that this vacuum state, this true vacuum state is lower energy than ours, then this is the false vacuum. This is the true vacuum. If we have this other state where the energy level is kind of lower, the Higgs field is higher, then something could happen that could kind of kick the Higgs field over that hill,
that threshold,
over that bump, and end up and put us over there. And so people used to worry about this with the Large Hadron Collider. They used to worry, like, what if you created an event that was so powerful that it kicked the Higgs field into the true vacuum,
like a small black hole? Small.
I mean, the black hole thing is kind of a separate question, but in principle, if you just had a really high energy event, you could excite the Higgs field. You could make it oscillate, and it would oscillate right over that hill. In practice, the energies you need to get over that hill are so high that it couldn't possibly happen. Like you can't do it with a machine, but also the kinds of energies that a machine like the Large Hadron Collider produces, those kinds of particle collisions are nowhere near as energetic as the particle collisions that happen in space with cosmic rays.
Yeah, cosmic rays.
So so even if we could, like, even if in principle we could reach those energies, then this would have happened billions of years ago, over and over and over again in the universe, because the cosmic rays are at higher energies anyway. So you'd think that we should be safe, right? Like, if we can't kick that thing over the hill, we should be fine. We're not going to end up, the Higgs field isn't going to go there.
Right.
But unfortunately, we live in a universe that's fundamentally quantum mechanical, which means that things like quantum tunneling can happen. And quantum tunneling is where, you have like a wall, and you have an electron on one side of the wall, and the electron, you don't need to get the electron over the wall. If you wait long enough, it'll just tunnel through the wall. It'll just sort of leak through the wall through quantum mechanics and end up on the other side. And the same thing can happen with the Higgs field. If you wait long enough, then the Higgs field in a false vacuum will quantum tunnel to the true vacuum.
Yeah, people are asking.
That's inevitable.
Yeah, people are asking, what's the difference between a true vacuum and a false vacuum? If you could define those.
Yeah, so a false vacuum is just a minimum in the potential that's not the true minimum. So if there's a deeper minimum, then that's a true vacuum, and the less deep minimum is the false vacuum. So any place where you have a shallow valley versus a deeper valley, the shallow valley is the false vacuum, the deeper value is the true vacuum, because the true vacuum is where the field really wants to be. So anyway, So what this says is that the Higgs field could spontaneously just show up in the other vacuum. And if it did, then what would happen is wherever that happened, like anywhere in the universe, where there is the Higgs field, the Higgs field is everywhere. The Higgs field at one point could transition from our vacuum, the false vacuum, to the true vacuum. And if it happened at that point, then what it would do is it would create a bubble around itself of this true vacuum space. And that bubble would expand at about the speed of light. And it would destroy everything in its path.
Right.
The bubble wall itself has some energy, so that kind of incinerates things. And then once the bubble wall passes over you, then you're in this space where your particles can't hold together anymore. And then once you're inside that space like gravitationally collapses and you end up in a black hole. So like you really don't want this to happen.
Yeah.
But in principle, if this is the way that the Higgs field is set up, then anywhere in the universe at any moment, the Higgs field could quantum tunnel and create this vacuum, and that vacuum would expand at about the speed of light and destroy everything in the universe. And there are a few reasons you shouldn't really worry about that, despite the fact that it could technically happen at any moment.
Well, it's rate of travel, right? So it's distance, right?
No, I mean that doesn't really help you. If it's anywhere in the kind of part of the universe that can interact with you, then it'll get to you because it's moving at the speed of light.
Then you won't even know. Then you don't even have time to think about it.
Yeah, but that's the thing. So you won't see it coming, right? Because if it's traveling at the speed of light, then by the time the light gets to you from it, it's already on top of you. So you don't see it coming.
Right.
You don't feel it when it hits you because your nerve impulses don't travel that fast. So in that sense, you definitely shouldn't worry about it. Also, there's nothing you can do.
Right.
But the other reason you shouldn't worry about it, though, is that the tunneling rate, the time it's likely to take for that tunneling to happen, is like 10 to the 100 years. So so on average, you would probably have to wait a really long time for it to happen. That doesn't mean it can't happen right now. It's just very, very unlikely to happen right now. But even beyond that, we don't know for sure that this true vacuum exists.
Right.
Our current understanding of particle physics, what the experiments tell us, suggests that probably that can happen. But also, what we know is that that this getting to this point requires extrapolating beyond the kind of limits of where we think that our understanding of particle physics is still valid. And so it's very possible that some other physics will show up when we have a better and more full understanding of particle physics that will tell us that actually this that other minimum doesn't exist and we're fine. But we don't know.
Yeah. And with those,
so it's a fun idea.
Yeah, with the smaller black holes, that would make one of these states unstable or unstable. Sorry.
Yeah. So if you could make a little black hole, that would make this tunneling a lot faster. Yeah. So you don't really want to make a little black hole because that if we are in a false vacuum, then a little black hole could kick us into the true one. But we don't know if it's possible to make little black holes at the moment. And if we could do it with a particle collider, it would have been done in space already. Mm-hmm. And we haven't died in a bubble of doom yet. So we can assume then that our particle colliders can't make little black holes that would destroy the universe.
Right.
So either we can't make little black holes or we don't live in a false vacuum.
Yeah, either
basically.
they popped into existence and popped right out and we're okay. We're still here.
Yeah.
Yeah, because that actually gets brought up a lot where people are like, what are they doing at the, LHC? Are they making these small black holes?
Well, there's really no way the LHC could be dangerous to us, right? Because anything the LHC can do, the universe already did, and we survived it.
Right.
So even if making little black holes was dangerous, it wouldn't matter because, it would have been done by the cosmos. Mm-hmm. And so if a cosmic ray hasn't done it, the LHC is definitely not going to do it. So it's one of these things that's like, we've never seen these collisions up close before in a particle detector, but that doesn't mean they're not happening out there in the cosmos. And if they're happening out there in the cosmos, then they're fine.
Right. Yeah.
I mean, in a cosmic sense anyway.
Right. And the rest of this, guys, I want to say for her book. So I read about vacuum decay, and again, there is a kind of balance, and I said this before you even came on, for a SciComm and also someone in science communication, someone that's also in research. So those two being married are very rare in and of themselves. But then like writing a book and having it make sense. So a lot of you guys have questions. Like there was one about saying, what is, they're wondering about the axes there. Like, so what does X and Y represent?
Yeah. So this is sort of energy in a sense. And this is the value of the Higgs field.
There you go.
This is a cartoon version of the diagram because the technical version is complicated. But if you're watching this and you're concerned because this is hard to understand, the book goes more slowly. Has more explanation, and
totally
I do think the book makes a lot of sense. Way it's done. So I think that I like don't be scared off by my inability to do this quickly on a blackboard on a stream. I think that hopefully it'll make much more sense if you sit down with it. But
no, it did to me.
Yeah.
And I went head first into it on the, just on the shallow end too. I was a little bit scared. I was like, I'm going to reach bottom real quick and this might be unsafe. But then my chat got to see my brain just be in a million different places because I still thought about that after the fact. So after I had read it, it's something that stuck with me pretty much that entire evening, even before bed.
Awesome.
So
so if that makes sense, if you can jump into chapter 6 and that makes sense, then that bodes very well because I do build on previous stuff from earlier chapters as well.
Yeah, I saw the chapters and I was going through, and so I kind of just perused those very quickly, and then because vacuum decay is just so cool. And out of all of these, like, what do you think's your favorite? Is it because I found vacuum decay to be much more like whoa.
Yeah, no, vacuum decay is totally my favorite, and you can have more than one, right? Like
of course. Sure.
Like you can have a heat death and then a big rip. You can have vacuum decay, on your way to a heat death. There are lots of you can combine things.
You can mix and match.
Yeah. But I think vacuum decay is fun because it's just this very dramatic, very sudden thing, and because we learn about it from particle physics, and because I wrote this paper about little black holes and cosmic rays and vacuum decay, and like in writing this paper, the one data point I used was the fact that the universe exists. Mm-hmm. Right. And that's just a fun thing to be able to work on, is to say, like, to work on a physics concept that would destroy the whole universe, and like to try and understand what's going on there, and to learn something from particle physics that could have such a huge impact on the cosmos. I think that's really fun.
Yeah. And you went to the LHC. You went there.
I did. Yeah. I visited CERN. I got to see some parts of the Large Hadron Collider. I got to see the
switch,
the CMS detector.
The switch.
Yeah. I got to hang out in the control room and look at the beam dump switch and all that stuff.
And how much a beam dump costs.
Yeah.
I was looking at that because I'm just in awe. Like, those are things that I would love to do. That's goals. But
it was super fun. It was a super weird trip to the LHC too, because to CERN, because I was there both as a physicist and as a science communicator. Mm-hmm. And so I was spending my time, like I spent part of my time in the theory group, like sitting in an office and meeting up with people for coffee and talking about vacuum decay and like talking about my dark matter research and giving a talk at the theory group about my work and all that. And then I spent part of my time with like the outreach people, getting shown around like a VIP in like the in the big experimental halls, wearing a hard hat, 80 meters underground, looking at these giant machines. And then I gave a talk to the CERN community about doing science communication, and then I gave a public talk to like for the public about the end of the universe. And so I was wearing like all these different hats, and it was just it was a very strange thing to go from like sitting in an office and talking to people about these extremely technical theoretical ideas, and then going deep underground wearing a hard hat, watching people with wrenches take apart things with wires, and like just those two extreme sides of physics. It was very cool.
Yeah. So do you have like 10 minutes for questions?
Yeah, I could do 10 minutes.
Yeah, 10 minutes is good. And then again, guys, like maybe there's some time we can have her back on. Dr. Katie can come back on, maybe in a more informal setting, if because usually I maintain a certain level of that. But like again, if there's something that you're just like, I don't mind talking about space tonight for an hour, like cool. I can come on, especially during this time, because I don't expect it to end much anytime soon. So, but yeah, so we can do, let me look at the clock. Okay. So 10 minutes. And again, thank you so much. And all of her information, guys, is in that command. Her website, which gives her CV. And well, I don't know if it does it. Does it say that you got your PhD from Princeton in there?
Maybe. If you go to the research tab on my website, there's a link to my like university page.
Yeah,
that has all that.
That's what I've looked at. So
yeah.
So you might not see it on like the splash page. You might have to dig. You might have to click things, guys.
I mean, I don't want to go around being like, here's my PhD from Princeton. Like it's not the most important thing.
True. Agreed. Okay, so let's do at Skylias. And guys, if I skip over it, it's not because I hate you. It's just, so what would happen if we're in a true vacuum, and would it quantum vacuum into a false vacuum, even in theory, if it's utterly impossible?
So the question being, if we lived in a true vacuum, could we end up could we tunnel into the false vacuum?
Yeah.
In principle, you could, but you would go right back. Like so if you go from a false vacuum to a true vacuum, then the bubble expands, and that's like, because it's sort of energetically preferable. It's like if you drop the end of a chain, it'll pull the rest of the chain down. You get a sort of similar thing, whereas you can throw a bit of a chain up onto a table, but it'll fall back down again because it would rather be at the bottom, right? So in that sense, going from a false vacuum to a true vacuum is like preferred. But if you're in a true vacuum, it can fluctuate up to the false one, but it'll fall back down again.
I'm going to interject my own question because you talk about this beautifully in your book. But someone asked yesterday, like, so these seem like conjectures when we talk about things that are, our future or our past, and people are very uncomfortable with being like, well, I don't really think that that's like, how do they know this stuff? Mm-hmm. And I gave them the example of saying, like, we know, like, for theory, there's mathematics that can support that, which is different than a hypothesis, like it's just a guess. So in this case, with all of this, like, what kind of tools do we use to come up with ideas about the future, taken likely from the past, right? There's some kind of symmetry that you describe in mathematics, the symmetry there, and how we like that symmetry.
Yeah. So for all of this stuff, for all the different sort of end of universe things, it's a mixture of looking at what's happening now in terms of the evolution of the cosmos, and looking at the very early universe and trying to understand how our universe was set up and what are the fundamental laws governing it. And the idea of symmetry definitely comes in a few different ways, but one way is that we often talk about the laws of physics in terms of the symmetries of the laws of physics. And symmetry sounds like a weird thing to apply to like mathematics, but when you study mathematics and you study like group theory and theoretical physics, you find that you can describe the equations that govern the interactions of particles and the laws of nature in terms of the symmetries that those equations work with. So like an equation can have a shift symmetry, which means that if you change the variable by some constant number, the equation still looks the same. And so that's like a translational symmetry or something like that. And there are all these different kinds of symmetries, rotational symmetries and things like that, where the fundamental laws of physics have certain inherent symmetries to them. And as physicists, we're always trying to understand the symmetries in nature and how those patterns fit together and what that tells us about how particle physics is structured, how fundamental theory is structured, gravity and everything like that. And so part of what we do as cosmologists is try to understand the symmetries and the laws governing the workings of nature.
Right.
And then we apply that to how the universe is evolving right now, what we see in the universe right now, and what we know about the beginning. And that can tell us about how the universe is going to evolve into the future. It's all conjecture at some point, right? Because we don't know what the future holds, but we can get, various degrees of certainty about what's going to happen.
Yeah. And good scientists don't claim to know. You're always at that blackboard right behind you, ready for anything to change, right? At any point, something can change, but that's a good thing. That's an exciting thing. Yeah. Change is not a bad thing.
Yeah, and in the book, I have a chapter about like how we're trying to figure this all out, and I go around and I interview physicists and cosmologists and astronomers who are working on all of these different aspects and try and get an idea from them of like what are they excited about, what kind of data are they going to get soon that's going to tell us something new, which way do they think it's going to go, how are we going to figure all this out, like and it was really fun to talk to all these different people and to get perspectives on where it's going and find out from people who are really on the cutting edge of like understanding the evolution of the cosmos, what tools they're using and how.
Right. I bet. Sorry, guys. I had to take up that one because, again, that was something I read in the book that made a lot of sense to me. So, again, these are things that are very well put that, again, it's a slower introduction leading up to the other things that get more complicated. That made me more comfortable with dealing with the complicated. So I can see that the Higgs field is a local minimum rather than a global minimum. Why is the word vacuum used into the description?
So we use the term vacuum to talk about like the background state of physics in a theory. So a vacuum in a theory is like how physics works in that theory. So you can have a different kind of vacuum state, and that just is a different setup of the physical laws, of the constants of nature, all of that. So we talk about a true vacuum and a false vacuum. We don't really mean vacuum in the sense of like nothingness. We mean like the foundation on which physical interactions happen in that theory. So it's kind of more of a theory than a theory in the sense of like a collection of physical laws than a vacuum in the sense of a nothingness.
And Neuro, that's a good question. I'm going to save that one for the end. So remind me here in just a few minutes. Within the limits of the theory of Hawking radiation, so the virtual pair particle popping in and out of existence, all that fun stuff, is there any solidity about what form the virtual particles will be in, being like baryonic matter, like us guys? Baryonic means us. We're baryonic matter. But I think they're actually talking about, is photon. Oh, okay. So baryonic kinetic or more quantum quant-like is photons or quarks.
So when a black hole decays, when it evaporates, what happens is that as the black hole is evaporating and it gets lower and lower mass, the evaporation, the Hawking radiation is higher and higher energy, and it produces heavier particles as you go. So when the black hole is just starting to evaporate, all it can do is release some like low energy radiation, and then as it gets hotter and hotter, as it's shrinking, it can produce more and more heavy particles, and so you get this whole spread of particles. And what kinds of particles, what kind of spread of particles, it takes complicated calculations to figure that all out. I'm working on a project right now with some colleagues where we need to know what particles are produced at different stages of a
leave
black
that
hole's
out because
evaporation.
that's the last question. I want to know about that. I want to know.
Okay.
Yeah.
Sure. I mean, this is anyway. So there are equations that govern what the spread of particles is, but basically, as the black hole evolves to lower and lower masses, the particles that it's producing are getting higher energy, higher mass, and you go through like basically the whole spread of all possible particles.
Is it possible dark matter existed before the universe?
So if you think that there was a previous cycle in the universe, if you're looking at a cyclic model of cosmology, then you can have matter that started in the previous cycle that can, some aspect of it can pass through. What we think probably happened with dark matter is we think that when this inflation period happened, when this rapid expansion happened, and then inflation stopped and the energy from that decayed into radiation, it also decayed into like all the particles that we know about, and dark matter could have been produced in that process, and so it would have been produced at the same time as everything else in the very, very early universe. And that would be sort of before the hot Big Bang, before the kind of fireball stage of the cosmos, but not before the beginning of the universe. But we don't know when dark matter was produced. We don't know exactly how it was produced. We don't know what it's made of. That's part of the big mystery. And there's another aspect, another project I'm working on with a student and another colleague at the moment that deals with when and how dark matter was produced in the early universe.
Yeah.
I don't know if you can hear it, but my foster cat just started meowing.
It's getting around that time.
Woke up.
Yeah. For my dog, that's actually not a foster anymore, but she's a retired racer. She's a greyhound.
Ooh,
so
cool.
She's a full-on adoption now, but
nice.
But at one point she was, and then they had to like go through that whole process of being like, it's okay, you have her. Yeah. But last but not least, I do want to know just what, I have like a million questions for you. I want to know all these things that people aren't asking right now. But maybe, if you're like, yeah, I have an hour and, I want to talk about space and less formally too. Like if you ever want to just like hop on here and again, like her opinions would be her own at that point, apart from talking about this, and that we've had guests on that are able to parse those two and separate them, and that's a wonderful thing. But for this, what are the projects you're working on research wise right now? You've already kind of touched on a few, but
yeah. So a lot of my research involves dark matter, and I have a project that I'm working on that has to do with dark matter that might have been present in the early universe, and in the early universe after the fireball stage was over and stuff was coming together to form stars and galaxies, the matter was kind of coming together in these clumps of dark matter, and if that dark matter had certain kinds of particle physics processes happening inside it, if dark matter can annihilate with itself and create radiation, then in those dark matter halos where the first stars and galaxies are forming, you'd have this little bit of radiation produced by the dark matter itself, and that could change how the stars and galaxies form. And so I've been working for a while on what the consequences of that would be on those first stars and galaxies. I'm also working on some aspects of vacuum decay, thinking about different consequences of ideas about vacuum decay in the context of the universe that we have now. And I'm working with some colleagues here in Canada on questions to do with little black holes. So we have a paper that's been published recently that was about whether or not you can create little black holes with neutrinos running into things inside neutrino detectors, And then if those black holes then evaporate, you get certain kinds of signatures in the light picked up by the neutrino detectors, and how you would be able to detect that, what that would look like. So we put that out recently, and we're doing some follow-up stuff on little black holes in the early universe that I don't want to talk too much about because it's new research.
Still in progress.
Yeah, it's work in progress. And I'm going to show you my cat.
Yeah, people are asking there. Can we see cat, please? That's Twitch for you.
Her name is Mochi.
Siamese.
She's a cute Siamese cat. She doesn't really like to sit on my lap, so she's going to jump away. But
she's going to be like, I'm done.
She likes to sit next to me. She has a little chair next to my desk.
Yeah.
That's hers. But anyway.
Yeah. No, you can see my Greyhound is over here on her own mattress.
Oh, nice.
She's awesome. All the way over there, but she has I never threw away my daughter's twin mattress, and that was a good call in the end.
Yeah.
But yeah, so thanks so much. And you know, like, again, there's so much, like, I had to tease the dark matter stuff because I know your research. So, but it would be great to have you on again. Like, if you're just like, sure. I'm totally fine with just hanging out.
I mean, I'm always happy to talk about physics and astronomy and cosmology and all that stuff. So it's just a matter of like setting up timing and stuff like that.
But like with the quarantine, I think there's a lot of more opportunity for SciComm. And so just talking about it and just enjoying the luxury of being able to be super comfortable with it. Yeah. And I think that's great.
I wanted, if you don't mind, I'll just put in another plug for my book. You can pre-order it. You can pre-order it now. There's links on my website, and either today or tomorrow, I'm gonna put up a link to a thing my publisher and I are doing, which is like a pre-order contest where if you pre-order the book and you can send us a little sort of pre-order number or something like that, then you get entered into a chance to get a special pin and a signed book plate, and I'm going to do like a Q&A video, and you can ask a question, and if it's selected, then you get this stuff. So there's this there's like perks to pre-ordering, and the big thing about pre-ordering is if you pre-order my book, then it goes toward first week sales, which goes toward like bestseller lists, and so it's like, this is why we do it, because it's helpful for me.
Oh yeah,
and to get that book out there into the world and stuff. But the perks will be cool too. So you know. Anyway, keep an eye out for that.
Yeah, it's so well written. Again, guys, like I went through each chapter and I was like, okay, like it flowed very, very well. I wouldn't recommend a book to my chat that I'd be like, guys, it's gonna be just. I'm gonna be pretty honest about it. So, but yeah, thanks for taking the time, and we'll catch up soon. Hopefully sooner.
Thanks.